Hey there, it's Shannon Matchick-Myers, and today we are covering section 2.4 from the ZIL text, and it's going over exact equations. So if you've seen my videos before, you know that I usually like to do proofs and stuff like that, but frankly, this section's going to be probably a little on the long side, pretty complicated, so I'm deferring the proof. You can look it up online. There's lots of different, actually they're all quite similar, and we'll just go ahead and truck through the material. So today our goals are to solve a first order differential equation written in differential forms, and then also we want to be able to use an integrating factor to solve an exact first order differential, and then we'll use partial derivatives to transform a non-exact differential to an exact. All right, so fasten your seatbelts. All right, now we'll be checking out first order differential equations written in differential form. And just as a reminder, differential form is capital M at x and y dx plus capital N at x and y dy is equal to 0. We just need to test the coefficients M and N to determine whether M at x and y dx plus, so this is an expression, N at x and y dy is the differential of some function f of x and y. So if it is, then we can construct some function f by partial integration. The differential of a function of two variables, if z is equal to some function of x and y, and it is a function of two variables with continuous first derivatives in some region R of the xy plane, then its differential is defined to be dz, and this, comes from calculus. Regular calculus is the first partial of f with respect to x plus the first partial with respect to y dy. And sorry, that's of f with respect to y dy. And these are partial derivatives. Okay? So, here we go. If f at x and y is some constant c, what would we have? Beautiful. If f of x and y was a constant, when you find the differentials, you would get 0 instead of dz. So we would have the first partial of f with respect to x dx plus that first partial of f with respect to y dy is equal to 0, which is a first order differential equation with one parameter. All right, exactly at our level here. So definition, a differential expression, m at x and y dx plus n at x and y dy is an exact differential in a region R of the xy plane if it corresponds to the differential of some function f at x and y defined in R. A first order differential equation of the form capital M at x and y dy, dx, excuse me, plus capital N at x and y dy equals 0 is said to be an exact equation if the expression on the left-hand side is an exact differential. So what does that mean? So here is a criterion, or the criterion for an exact differential. Let m at x and y and n at x and y be continuous and have continuous first partial derivatives in a rectangular region R defined by a is less than x is less than b and c is less than y is less than d. Then a necessary and sufficient condition that m at x and y dx plus n at x and y dy be an exact differential is that the first partial of m with respect to y has to be equal to the first partial of n with respect to x. Okay? So, here we go. For our first example, we want to figure out whether the given equation is an exact equation. So here, my apologies, this was supposed to be a little bit different. It's supposed to have an addition sign and it's equal to 0. And we will have one a little bit later that will be affected. I have an evil plan. All right, perfect. So here, what do we need to do? We need to take a look, identify our m, which is 1 plus natural log at x plus y over x, and find that first partial of m with respect to y. So in this case, you hold the terms that don't have any y's, they're constants, and so we're going to end up getting 1 over x for this one. Now, n is equal to -1 plus natural log at x. You do need to make sure that you have it in the format of this differential. So m at x and y dx plus n at x and y dy equal to 0. You might need to make an adjustment with the sign. And so finding the first partial derivative with respect to x of n gives us 1 over x. So they match. We're good to go since dm dy equals the first partial of n with respect to x. That means the equation is exact. Cool? All right, so let's check this one out. We're going to have to do a little bit of work on this one. We're going to need to multiply through by dx. And when we do so, we will have the quantity 2y minus 1 over x plus cosine at 3x dy plus, you see the rest of the terms can be grouped with the dx. So I'm going to start my parentheses, and we'll have y over x squared minus 4x cubed plus 3y times sine at 3x times dx, and then 0 times dx is still 0. All right, what do you think? Are we good to go? Be careful. Remember, the dy term is first, so let's just rewrite this real quick. We're going to end up with y over x squared minus 4x cubed plus 3 times y times sine at 3x, all of that times dx, plus 2y minus 1 over x plus cosine at 3x times dy equals 0. Now we can identify m as 4 over x squared minus 4x cubed plus 3y sine at 3x. Finding that first partial of m with respect to y, we'll get 1 over x squared, and then the second term zeroes out, and then the third term, be careful, we'll have plus 3 times sine at 3x. Now looking at n is equal to 2y minus x to the negative 1 plus cosine at 3x, and finding the first partial of n with respect to y, we will have, with respect to x, we will get a result of positive 1 over x squared minus 3, using the chain rule, sine at 3x. So almost the same, but not quite. We've got a different sign in between them. And so we would say no, since dm dy is not equal to dn dx. All right, so now continuing, let's just take a look at this method here. Method to our madness. All right, so the method for solving an exact equation. Now this is going to seem a little vague, and I'm kind of splitting it apart. It's a little bit of a confusing process until you've done a few of them. So first of all, determine whether it's exact. So is the first partial of m with respect to y equal to the first partial of n with respect to x? If it is, you can move on. If not, I show you a method where you can use an integrating factor, but you know, you might want to check out another method if it's not. So set up the differential equation either df dx is equal to m at x and y, or the first partial of f with respect to y is equal to n at x and y. So if you do the first one, for the first partial of f with respect to x equal to m at x and y, what you do is you find f by integrating m at x and y with respect to x while holding y constant. So this is what you would have. You would have your function f, you could write it as f at x and y, is equal to the integral of m at x and y, okay, dx, and then you're going to get plus g at y. So this one here, g at y, is your integrating factor. So the arbitrary function g at y is your quote-unquote constant of integration. Now, if you set it up where you have df dy equal to n at x and y, you want to find f by integrating n at x and y with respect to y while holding x constant. So you'll end up getting f at x and y is equal to the integral of n at x and y dy plus some h at x as our constant of integration. So h at x is your constant of integration. Groovy? Okay, then you differentiate your result from this last step with respect to y for the way we set it up in 3a when we held y constant, and we assume that the first partial of f with respect to y is equal to n at x and y. You differentiate your result. If you did the setup for 3b, you're differentiating with respect to x and assume that the first partial of f with respect to x is equal to m at x and y. All right, so then you get the results that you get for these are, okay, so when we differentiate, we're going to end up getting the first partial derivative of f with respect to y, which is equal to capital N at x and y, would equal to the first partial with respect to y of this integral that we had gotten, which was beautiful, capital M at x and y dx, and then you're going to end up with this constant, the derivative of g at y, which is just g prime at y. And for the second one, you would find that first partial of f with respect to x, and that of course is equal to capital M at x and y as we set it up to begin with, and that in turn will be the first partial with respect to x of the integral of n at x and y that we had gotten in that step, dy plus h prime at x. I know it seems really abstract right here, but it's kind of cool when you do it. Then, after you get h prime at x, you isolate your h prime at x or your g prime of x. And then you go through and then you integrate. So if you set it up like the part A's, you would integrate with the result from step 4 with respect to y, if you did it by 4a, and then you substitute the result in the equation from step 3a to get the implicit solution, f of x and y equals 2 sum c. So you basically, when you put all this together, you're gonna find your g of y. You're going to plug it back into 3a and you'll get your solution. And you would do it in terms of x if you did it the part B way, and then you'd still have f at x and y equal to some c. Groovy? Okay, so let's look at an example. So again, I told you I had an evil plan about this. So here we go. Step 1, we got to figure out if the first partial of m with respect to y is equal to the first partial of n with respect to y. All right? Or with respect to x, my bad. I'm writing it correctly. Okay. Now, is it in the right format? Yes. And we checked this in step 1. All right, we did this in step 1, so we're good. Now, step 2, is when we set up our differential equation. Okay, so let's actually write down what our m is and the partials and all that. So m was equal to 1 plus natural log at x, and m, of course, is equal to the first partial of f with respect to x. We've set it up that way. Cool, cool? And m is in terms of x and y. And the first partial of f with respect to y is equal to n in x and y. And that was equal to -1 plus natural log at x. Oops, I don't need the parentheses on this. All right, so we're good to go. Ready? So now for our second step, what we're going to do is we're setting up our df. I'm going to choose df dy, the first partial of f with respect to y. I don't know, it just looks nice and easy to work with. It doesn't matter which one you pick, so you decide, you do you. And we're setting this equal to n in terms of x and y. That's the whole setup. So we'll have df equal to capital N in terms of x and y, dy, and finding the partial and doing the partial integral with respect to y. Let's see what happens. This one's just going to be f, or f of x and y. We know what n of x and y is, right? So let's plug that in. We're going to get -1 plus natural log at x, but we're integrating with respect to y. So I'm just going to write it as dy. And then f will end up being -y plus y times natural log at x, and then plus we're going to have some function of x, call it h of x. Cool, cool? All right, so in that third step, remember, we were we want to find h prime of x. So in step 3, we are going to find the first partial of f with respect to x now, because you do it with respect to whichever variable your constant is in terms of. And so that's going to be equal to the first partial with respect to x of all the stuff we got from the last step. -y plus y natural log at x plus h at x. All right, well, what was df dx? Remember, df dx is equal to m, and m was 1 plus natural log at x plus y over x. So I'm going to write that in. All right, and then set it equal to this partial derivative. The first term zeroes out. Second term will get y over x plus h prime of x. Cool, cool? Now, isolating h prime at x, do you see that the y over x is 0 out? And so we'll just be left with 1 plus natural log at x. Groovy? All right, perfect. Next step. Lots of steps here. People like steps, don't they? All right, so next step, we want to integrate h prime of x with respect to x. So when we do that, what's going to happen? Well, h prime of x will just be h at x, correct? And then we'll have the integral of 1 plus natural log at x, that quantity, times dx. All right, don't forget all of your wonderful math skills from before. We've got an integration by parts problem for part of it. So this is going to be x plus the integral of natural log at x dx. And if you let u equal to natural log at x, that's the only choice you have, because it doesn't have, a simple integration formula, natural log at x. So the derivative will be 1 over x dx. We'll have dv, it's just equal to dx, so easy, it's hard, and we'll get v is equal to x. Now, continuing on with our antiderivative here, we will have, I'll just keep writing my h of x. So h of x will equal to x plus, so remember integration by parts, you do u times v, so I'm going to write it as x times natural log at x minus the integral of v du, x times 1 over x dx. So the x's divide out to be 1, so h at x will equal to x plus x times natural log at x, and then you'll just get minus x. We will leave the constant for when we solve the final problem. So h at x actually simplifies to be x times natural log at x. I think my steps are kind of off. So step 2 was setting up the equation. Step 3 was actually right here, the integration portion. So then we'll have step 4 for the derivative portion, and then we're currently on step 5. So now we go back to our equation from step 3 and back substitute what we found here. So remember that f at x and y was set up to be some constant, right? And in for f, we are putting in negative y plus y times natural log at x. And in for h of x, you put what you found for h of x, which was up here, x ln x. Cool? And so, just to clarify, we plugged in x times natural log of x for h of x, because that's what we found for it. And we're done. That's the final result. So we get negative y plus y times natural log at x plus x times natural log at x equals some constant c. Groovy? All right, on to the next. So here we go, our next problem. I'll let you read it. So what do we have to do first? What do we have to do first? Oh, and gosh, I don't know what's wrong with me. I have a typo in this one too. This cosine is supposed to be cosine at x. Cosine at x. All right, so first off, let's rewrite this problem so it's in the right format. So we'll have 2y times sine at x times cosine at x minus y plus 2y squared e to the xy squared, all of that times dx. Now, plus, but you're going to have to change the sign on everything. So I'm going to distribute the negative through because we got to get it on the other side of the equation. So we're going to have negative x plus sine squared at x plus 4xy e raised to the xy squared, all of that times dx is equal to 0. Cool, cool? All right, so step 1, we got to make sure we can do this, right? So step 1, let's figure out what all our stuff is and all that good stuff and make sure that dm dy equals dn dx. So here, actually I'll put our list over here. dm dy will be m is equal to df, the first partial of f with respect to x, and that's going to equal to 2y times sine at x times cosine at x minus y plus 2y squared times e to the xy squared. And then my first partial of f with respect to y is equal to n of x and y, which is equal to negative x plus sine squared at x plus 4xy e to the xy squared. Cool, cool? So, treating the x's as constant for m, I'm going to get what? Beautiful. 2 times sine at x times cosine at x, and then minus 1 and plus, what do we have to do here? Awesome. We got to do the product rule, right? So I'm going to look at the first term as 2y squared. So we'll have 2y squared times 2xy times e to the xy squared plus 4y times e to the xy squared. Cool so far? All right, now we got to see what is the first partial of n with respect to x. So when I do that one, I'm looking at n, differentiating with respect to x. I will get negative 1 plus 2 times sine at x times cosine at x. That's for the sine squared at x. All right, using the chain rule. And then I'll have to again use that product rule, right? So we're going to have plus 4xy, differentiating e to the xy squared with respect to x. I will have, beautiful, times y squared e to the xy squared. And then differentiating that first term, we'll have 4y times e to the xy squared. Groovy? So let's match the terms. 4y e to the xy squared, those match. 4xy cubed e to the xy squared, those match. Once you simplify, those two would match. And then we've got the 2 times sine at x times cosine x and the negative 1s. So they match. We can continue. Aren't you lucky? All right, so now on to step 2. Step 2, We were just setting up that equation. I'll make sure and do my steps right. So here, you just got to decide which one you want to deal with integrating. I'm looking at that first one. Neither one of them is horrible. You just need to decide what looks appealing to you. I think I'm going to go ahead and use m of x and y, okay? So I'm going to set up that equation. The first partial of f with respect to x is equal to m in terms of x and y. And so first partial of f with respect to x, what was m of x and y? It was 2 times y times sine at x times cosine at x minus y plus 2y squared times e to the xy squared. Groovy? Okay, so now on to step 3. We're going to do our integration. All right, so df, we're going to integrate df. It's going to equal to the integral of all this good stuff. And we're integrating this with respect to x, Cool, cool? All right, so this is going to give us that our function in terms of x and y, or just f, whatever you want, will be. So we're integrating with respect to x. The y's are treated as constant. So the 2y is going along for the ride. Now, do you see that cosine x is the derivative of sine at x? Sine at x is to the first power. So we're going to end up having sine squared at x over 2, using that general power rule. We've got the first term done. Minus x times y, we got the second term done. Now, notice that the derivative of the power in that exponential term is available for us to use. So the derivative of xy squared with respect to x is just y squared. So we will have plus 2, and then we'll just get e to the xy squared. Beautiful. And we've got to remember to add our constant of integration in terms of y this time. So f of x and y will simplify to be y times sine squared at x minus xy plus 2e to the xy squared plus g at y. Whoops. And now we are on to our step 4. Exciting, exciting. What color did I do step 4 in? Blue. Perfect. All right. So for step 4, we now need to differentiate find the first partial of f with respect to y, so that we can start finding g at y. And we will have df dy equals. So sine squared at x is treated as constant, right? And then, so when we differentiate y times sine squared at x, we'll just get sine squared at x, and then minus, beautiful, x, differentiating the term xy with respect to y, and then differentiating 2e to the xy squared with respect to y, we will have, beautiful, we will have 4 from the 2's multiplying out, so 2 times 2xy, so we'll have 4xy e to the xy squared, plus g, and apologies, this should be in terms of y, g at y. Alright, I'm going to go ahead and add. Alrighty, so here we go. Continuing. This will be, now what was df dy? Remember it was n, which was all of this stuff up here, right? So, df dy equal to n, probably have to go back a couple times. So we'll have negative x plus sine squared at x plus 4 times xy e to the xy squared. Let me double check that, and then I'll highlight it to show you. Alright, so this was our n. I think we're good to go. So we'll have sine squared at x minus x plus 4xy, oh, and this was g prime, we've already differentiated, 4xy e to the xy squared plus g prime at y. Now we want to get g prime of y alone, so let's see what zeroes out. The sine squared at x terms zero out because they have the same sign, so do the minus x's. Ooh, so do these. So it turns out that g prime at y is 0. Well, that means if you integrate both sides with respect to y, which is step 5, correct? Was when we integrated. I did that in the kind of pink color. I'll just show the work. So step 5, we want to find the integral of both sides. So sorry, you'll just get g at y equals the integral of 0 dy. So g at y is 0. And then continuing to back substitute, remember we're looking at that equation in green, right? So we'll have, at the end of the day, f of x and y equals c equals y times sine squared at x minus xy plus 2e to the xy squared plus 0, and then that gives us y times sine squared at x minus x times y plus 2e to the xy squared is equal to c. Cool, cool? All right, there we go. Second problem down. You're doing great. Hang in there. Pause the movie if you need a break. All right, here we go. Now we've got this in terms of an initial value problem. So let's, you start off the same. We're going to rewrite this so it's in the correct format. Instead of dy dx, we have dy dt. So we will have, I'm going to simplify this fraction. We're going to end up having 3y to the negative 3 minus t squared times y to the negative 5, all of that times dy, And don't forget, we're going to need to switch them around. So actually, if you don't mind, I'm going to pull this one over here. We're multiplying both sides of the equation by dt. And so we will have t, I'll say 1/2 times t times y to the negative 4 dt. So, and now we'll be set up. Cool, cool? So, all right, step 1, identifying our m as 1/2 t y to the negative 4. And remember that that's the same in this case as df dt. And then df, first partial of f with respect to y, is n, which is equal to, beautiful, 3y to the negative 3 minus t squared times y to the negative 5th. All right, let's get it going. So step 1, we need to find out if dm dy, right, what that is equal to, and see if it matches the first partial of n with respect to t. So looking at m and differentiating with respect to y, we'll get, I believe, negative 2 t y to the negative 5. Cool with that? All right, and then let's take a look at dn dt, first partial of n with respect to t, and that's going to give us, oh, let's check it out. The first term zeroes out, there's no t's in it, and then the second term we'll get negative 2t y to the negative 5. So they matched, they're a match. So we get to complete the problem. Awesome. All right, so now we're on to step 2, setting up our equation. So again, let's just take a look at m and n, and let's see what we want to work with. So on this one, I think I'll work with df dt. So we're going to set up df dt is equal to m, and this time it's in terms of t and y. And so df dt is equal to, actually set it up like this, so we'll get df is equal to 1/2 t times y to the negative 4 dt. Cool, cool? All right, third step, integrating. So when I integrate with respect, when I evaluate, the integral of both sides, I will get f of t and y is equal to, let's see, so I'm integrating with respect to t, so I believe we'll have 1/4 t squared y to the negative 4, and then plus some constant g at y. Groovy? All right, so now what do we need to do? These are easier, a little bit easier so far, right? Now we need to go to our step 4, which was in our blue. Try to remember. And now we need to find the first partial of f with respect to y. And we will get On the left side, don't forget that that's equivalent to n. So n was 3y to the negative 3 minus t squared y to the negative 5. And then on the right side, what's going to happen? Beautiful. So I will have the negative 4 divided by 4 becomes negative 1, right? So I'll have negative t squared y to the negative 5 plus g prime at y. And working through it, the signs are the same on those two terms there. And it looks like g prime at y equals 3y to the negative 3. Cool, cool? All right, now step 5. Let's wrap this bad boy up and apply that initial condition. So I'll go along over here for our step 5. All right, so integrating both sides with respect to y, we're going to get g at y is equal to the integral of 3y to the negative 3 with respect to y. G at y equals, increasing the power by 1 and dividing by that number, we'll have negative 3 halves y to the negative 2. And plugging that in to our equation from step 3, we will have f at t and y equals c, which equals to 1/4. Actually, I'll write these with positive exponents. So we'll have t squared over 4y to the 4th minus, because it's negative on that g at y, we'll have 3 over 2y squared. Now, applying our initial condition. So remember that our initial condition, y at 1 is 1. So y at 1 is 1. So that means that we'll have 1 squared over 4 times 1 to the 4th minus 3 over 2 times 1 squared is our constant. And that will give us 1/4 minus 3 halves is our constant. And that's going to give us, beautiful, negative 5/4 is our constant. So putting it all together, we will have t squared over 4y to the 4th minus 3 over 2y squared equals negative 5/4, and we're all done. Beautiful. All right. Moving right along. Okay, hang in there. Now let's just take a look here. This is kind of leading into the integrating factor. So let's check out this problem and figure out what value of k would we need to have for this given differential to be exact. Okay, so checking this out, you see that m is equal to 6xy cubed plus cosine at y. So the first partial of m with respect to y will be 18xy squared and then minus sine at y. Now n is equal to 2k x squared y squared minus x times sine at y. And then finding the first partial of n with respect to x would give us 4kx y squared minus sign at y. And so now we need those to be the same, correct? So everything is the same except for the coefficient to the xy squared, right? So if we were to set these folks equal to each other, the 18 equal to 4k, we would have the same thing. So if we set 18 equal to 4k, that's going to be 9/2 is k. So if k was 9/2, then this would be an exact equation. So using integrating factors in an exact differential equation problem can be challenging. I'm going to try to keep this pretty low key, okay? So for an integrating factor, if it turns out that the first partial of m with respect to y is not equal to the first partial of n with respect to x, it's sometimes possible to find an integrating factor so that after multiplying we have an exact differential. At this level of differential equations, we assume that we have some mu, which is a function of one variable. Okay, if you go higher, you can get it more complicated. So if mu is a function of x, okay, then what we will have is d mu dx is equal to the first partial of m with respect to y minus the first partial of n with respect to x all over n times mu. Cool? Now, if mu is a function of y, we will have d mu dy is equal to, and these are actually, sorry, I'm using these are partial derivatives. So I should have the curlier. Been a little bit of a day. All right, so this would be the first partial of mu with respect to y would end up being nx minus my, so first partial of n with respect to x minus first partial of m with respect to y, all divided by m times mu. Now, here's the bad news. You might need to try both to see which expression depends solely on one variable. So it turns out your integrating factor, if it's the first case, will be e raised to the coefficient of that mu. So you'd have the first partial of m with respect to y minus the first partial of n with respect to x divided by n, and you would be integrating that with respect to x. That's for this expression here is a function of x alone. And the other way would be e raised to the first partial of n with respect to x minus the first partial of m with respect to y all over m, and that's going to be with respect to y, and that is for when all of this here is a function of y alone. How do we use this? Okay. Well, fortunately for you, or unfortunately, depending on how you're feeling, you'll have an example. All right, so here we are, example 5. Please solve the given initial value problem. And to solve it, we're going to find an appropriate integrating factor. Cool, cool? Okay, so here we go. Oh, this one I actually corrected, but I'm sorry, it's... Oh no, we're good. I was seeing all these equal signs. All right, perfect. So here we go. If you look at, I'm going to just call it, M1, okay? So if we look at M1, we have x squared plus y squared minus 5. And if you were evaluating the first partial of M1 with respect to y, you would get 2y. And then if you think of our other expression as n1, so be careful because it's on the other side of the equation, right? Or equal sign. So you would have to add, and then you'd have negative y minus xy dy equals 0. And so your n1 would be negative y minus xy. And then if you found the first partial of that with respect to x, we would have what? Good, negative y, right? And they don't match. So, as it stands, it's not exact. Okay, so now what we need to do is try to get this to be exact. So you try both of these expressions if you have to. I'm just going to start with this one because it's first, okay? So I'm going to look at the first partial of m with respect to y minus the first partial of n with respect to x, divide through by n, and see if it's a function of x alone, okay? So if it is, we're good, and we'll be able to continue, and if not, we try the next expression. All right, so when we do this computation, right, we're gonna get what? Beautiful. We'll have 2y and then minus negative y over, so n was, I'm going to factor out the y, the negative y, and we'll have 1 plus x. Cool, cool. And then that, it's looking good, will be 3y over negative y times 1 plus x, which in turn will give us a function of x alone. Woohoo! All right, the y's divide out, don't lose that negative, so we'll have negative 3 over the quantity 1 plus x. Our integrating factor will be e raised to the integral of negative 3 over 1 plus x with respect to x. And that is equal to e raised to the natural log, and then, sorry, we've got negative 3 going along for the ride, of 1 plus x. And then this in turn will be e raised to the natural log of 1 over 1 plus x cubed, which is just 1 over quantity 1 plus x cubed. Cool, cool? I recognize we're supposed to have the absolute value of this, but for purposes of this exercise, just trust me, we're good. Okay? All right. Now, this will allow us to have a new m and n. Okay? So, now we are going to have our m, and we're basically multiplying both sides of the equation by 1 over 1 plus x cubed. So our new m will be x squared plus y squared minus 5 over 1 plus x cubed, because if you multiply by 1 over 1 plus x cubed, you get that for m. And then our new n, and remember that this is our df dx, okay? And our new n will be equal to the first partial of f with respect to y will be n, and that new n is going to be negative y minus xy divided by 1 plus x, the quantity cubed. So just to clarify, I multiplied both sides of this equation by 1 plus x, the quantity cubed, and sorry, it's 1 over 1 plus x, the quantity cubed. Groovy? Okay, so now here we go. Let's do this thing. So when I take a look, we still want to do our first step, which is, you know, we had a step 0 on this one to make it work. But our first step is we got to check, does the first partial of m with respect to y, is that equal to the first partial of n with respect to x? Okay, so let's verify to make sure we did it right. If we set this up correctly, then it's perfect. Okay, so first partial of m with respect to y, that denominator is in terms of x, we don't have to worry about it, so we'll be left with 2y over the quantity 1 plus x cubed. And now let's take a look at the first partial of n with respect to x, and we will have, let's see, the minus y part will zero out, right? So let's actually, I'm going to simplify n in order to do this. If we factor out that negative y, we'll have 1 plus x over 1 plus x, the quantity cubed. This one divides out completely, and then the denominator becomes squared. So that's a lot simpler, right? We'll end up getting positive 2y when we multiply by negative 2 over 1 plus x to the third. Groovy? So, yay! All right, so now here we go. Let's do this thing. Step 2. All right, which equation do we want to use? I don't know about you, but think I'm kind of liking n. Okay, so we're going to take a look at df dy, which is our n, and n is in terms of x and y this time. And so we're going to have the following. All right, perfect. And then now we're going to want to integrate. So step 3, completing that integration, we'll get f in terms of x and y, or just f, whatever you feel like, is going to be the integral. So what was our n? It ended up being negative y over quantity 1 plus x squared, and then we're integrating with respect to y. So that will be equal to, we're treating the 1 plus x squared as a constant, so we'll get negative, we'll say y squared over 2 times 1 plus x, the quantity squared, plus some constant some integrating factor h of x. All right, so now we go to our next step, which was, what was our next step? What color was I using? It's been so long, I forgot. All right, blue, perfect. All right, so our next step, we are going to now differentiate what we found. So remember that we're going to find the first partial of f with respect to x, right? All right, so we had negative y squared over 2 times quantity 1 plus x squared. Be careful you don't mix up those powers. There's a lot of different powers running around. Plus h of x. Now, what was our df dx? Well, if you look back up here, df dx is m, right, our new m, which is x squared plus y squared minus 5, that quantity, over 1 plus x cubed. That's equal to. So now, when I multiply by negative 2, I'm going to get a positive y squared over quantity 1 plus x to the negative 3. Nope, to the positive 3, since I'm writing it in the denominator, plus h prime at x. Then partially splitting this fraction, do you see we'll have x squared, or actually I have the same denominator, so I'll have x squared plus y squared minus 5 minus y squared all over 1 plus x, the quantity cubed, is equal to h prime at x. So h prime at x equals x squared minus 5 over 1 plus x, the quantity cubed. And you're so lucky because I picked a problem that requires partial fraction decomposition to integrate. Isn't that awesome? All right, so integrating with respect to x, step 5. We will have h at x equals to the integral of x squared minus 5 over quantity 1 plus x cubed with respect to x. Now, doing the partial fraction decomposition on the side here, we will have x squared minus 5 over 1 plus x cubed equals a over 1 plus x plus b over, because it's a linear factor and it's raised to a power, so you got to represent every power. And then over c over 1 plus x, the quantity cubed. Getting a common denominator and equating the numerators, we will have, you got to multiply a by 1 plus x, the quantity squared, which is 1 plus 2x plus x squared. We got to multiply b by 1 plus x, and c already contains the common denominator. We'll have x squared minus 5 equals to a plus 2ax plus ax squared plus b plus bx plus c. And then we've got 1x squared plus 0x's minus 5 equals 2. I only have an a as a coefficient to the x squared term. I have 2a plus b as a coefficient to the x term. And then our constant term is a plus b plus c. And then equating coefficients, a will equal to 1. 2a plus b is going to equal to 0, and a plus b plus c is equal to negative 5. Substituting in a equal to 1 into the second equation and solving for b yields a result of b is negative 2. Substituting a is 1 and b is negative 2 into the third equation gives us that c is negative 4. So we can rewrite our h of x here. We'll rewrite the integral as the quantity 1 over 1 plus x, substituting in for a, and then minus 2 over 1 plus x, the quantity squared, and then minus 4 over 1 plus x, the quantity cubed, all being integrated with respect to x. So h of x will be natural log absolute 1 plus x. We'll have that absolute value now. And then we will have minus, let's see, we're going to increase the power by 1, which would be negative 1, and then divide by negative 1. So that turns to a positive. And when you and we'll still have 2, and that'll be over 1 plus x. And then similarly, we'll have a positive here. We'll have a coefficient of 2, and we'll have 1 plus x, the quantity squared, in our denominator. Cool, cool? All right, now remember what we found way back when in step 3. F of x and y, I'll just copy this one, was equal to all this. And so, plugging in h of x into this equation, setting f of x and y equal to c, we will have negative y squared over 2 times 1 plus x, the quantity squared, plus h of x is all of this stuff we just found, natural log absolute 1 plus x, plus 2 over 1 plus x, plus 2 over quantity 1 plus x squared. We had an initial condition. So our initial condition was that when x is 0, y is 1. So y at 0 equals 1. That will yield C equals negative 1 squared over 2 times 1 plus 0, the quantity squared, plus natural log absolute 1 plus 0, plus 2 over 1 minus 0, plus 2 over quantity 1 minus 0, 1 plus 0, quantity squared. And where did I get that? I'm plugging in 0 wherever I see an x. And then wherever I see a y, I'm plugging in a 1. So this simplifies quite a bit. This simplifies to be C equals negative 1/2. Natural log at 1 is 0. Plus 2 plus 2. So C will be 7/2. And putting it back together, we will have negative y squared over 2 times 1 plus x, that quantity squared, plus natural log absolute 1 plus x, plus 2 over 1 plus x, plus 2 over quantity 1 plus x squared equals 7/2. There you have it. All right. Well, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please hit that like button and subscribe. Bye.